Okay, good morning. How's everybody doing? Um, so our plan, we're going to finish the chapter today. On today's Wednesday. So we're going to finish the chapter today. Tomorrow we have class, and we're going to, first I'll spend time answering questions that you might have, and then we'll get a start on the next chapter. Friday we'll have a quiz that'll cover, probably a chain rule type of problem, an implicit differentiation problem, which we did today or yesterday, and one problem on higher derivatives, which we're covering today. I'm going to get those back to you by like Monday midday. I know there's one person who will be out, but they're going to make arrangements to take that quiz on Monday, so I want to make sure you can get those back so you have some feedback before you come on Tuesday to take the test. Are there questions that you have on either practice exercises or the problem set or any of the examples we covered last time? Okay. Well, hearing none, I'll just, we'll go ahead and get started. Okay. So, what we're doing, there's no new techniques in this section. Really, we're just kind of defining what higher derivatives are, but the way we find them is precisely the same way that we've been finding all of our derivatives. So let's, we're going to start with this function, y equals 5x cubed minus 2x. We could find y prime, which is also the same as dy dx, right? We have these two different notations. It's a polynomial, right? So this is a pretty simple one. Applying the power rule here gives us 15x squared minus 2. That's the derivative of y. We also call it the first derivative. And of course, that name suggests that there might be other derivatives, and there are. So this function that we have for y prime is a function in its own right? This 15x squared minus 2, that's a function of x. We could take its derivative. So when you take the derivative of the derivative, we call that the second derivative. We denote it with a double tick, the y double prime, or using the other notation, d squared y over dx squared. Notice the position of these superscripts. The 2 up top here on the d means I'm taking the derivative twice. That's a second derivative. The 2 superscript on the x down here means I've respected x both times. It's with respect to x each time. If we take that derivative, again, we're just taking the derivative of 15x squared minus 2. We use the power rule. We get 30x. That, of course, is a derivative, or is a function itself. So we could take the derivative again. We can keep going, right? So we get our third derivative, d cubed y over dx cubed. We just get 30. And then we have one more. Now, you keep taking derivatives, right? So you can imagine that, using the prime notation, we just have like a bunch of tick marks. Usually once we get past the third derivative, we switch that notation and we write as a superscript the number in parentheses, because I don't want to confuse it for like raising y to a power. But in parentheses, y to the fourth, that means it's the fourth derivative. And then we get 0. If the original function we start with, like we started with 5x cubed minus 2x, that's a polynomial. If you start with a polynomial, so that means just positive integer powers on x, you'll eventually get to 0 when you take the derivative. And if you have a polynomial of degree n, there are precisely n non-zero derivatives. So our third derivative, we started with a polynomial of degree 3. Our third derivative was the last non-zero derivative we got. As soon as we got to the fourth derivative, we got to 0. And of course, all the derivatives thereafter will be 0, right? If you take the derivative of 0, you get 0. That's only true for polynomials that you eventually get to 0. If it's anything else, usually you just keep going. You keep going forever and ever. So let's find the higher derivatives of this function. Now, when they say find the higher derivatives, what's implied is that they want you to find all of them. And if they want you to find all of them, that means that what they've given you is a polynomial, and that you'll eventually get to 0. This is a polynomial. If I expanded the whole thing out, it would be a polynomial of degree, 4, 5. And in fact, we could start by taking the derivative and applying, like the product rule. I think it might actually just be easier to FOIL this out and expand. And then we could just, use the power rule the whole way down. You could really take your pick, though. If you like the product rule, you could use that. So f of x is x times, if we FOIL this out, we get x to the 4th minus 2x squared plus 1, and then we can distribute the x. So there's f of x. And then we just start taking derivatives. F prime, 5x to the 4th minus 6x squared plus 1. Our second derivative is 20x cubed minus 12x. We can keep going. Our third derivative is 60x squared minus 12. Our fourth derivative is 120x. Our fifth derivative is 120. And now all the rest of them are 0. So the way that we would write that is that the nth derivative, so I'm putting the little n in parentheses as a superscript. The nth derivative of x is 0 for n greater than or equal to 6. So those are all the derivatives. Are there questions on that example or about, what we mean when we talk about higher derivatives or? Okay. All right, well, we'll try another one. So here they asked us to find f double prime of -2. So what we're going to do first is just find f double prime of x as a function, and then we'll evaluate it at -2. In order to find f double prime of x, we first have to find f prime of x. So I'm going to start, when I look at this function, there's a couple ways we could find the derivative. And you'll get the same correct answer either way, but one way is a little bit easier than the other. So I notice that there's no x on top, right? It's just a constant on top. So if I start by just rewriting the function by bringing that 1 minus x up top to the -1 power, now I don't have to use a product or quotient rule. What do we get when we take the derivative? What do we get for f prime? Or who wants to start us off?
Negative. Times 1 minus
Sorry, times 1 minus x to what power?
2.
To the -2 power? And then times -1? Yeah, so then I'll just clean this up a little bit. We have now a +2, 1 minus x to the -2. So there's f prime, and I'm going to leave it in that form because I want to find f double prime. And again, notice I don't have to use the product rule or anything here, right? There's only one of the factors that has an x in it. Who wants to start us off finding the second derivative?
Negative 4
Mm-hmm.
times 1 minus x to the negative squared power times negative 2.
Times what? I don't think it's a negative 2 that we're going to multiply by. Yeah, negative 1, because that's the derivative of the stuff inside. So we get a positive 4 times 1 minus x to the negative 3. Now we're going to evaluate this. So for convenience of evaluation and just a nice sort of simplified way to express the derivative, I'm going to adhere to the convention of avoiding negative exponents. So I'm going to call this 4 over 1 minus x cubed. There's our second derivative. And now we can evaluate it. We can plug in negative 2. So f double prime of negative 2, 1 minus negative 2 cubed. 1 minus negative 2 is 3. 3 cubed is 27, so we get 4 over 27. Now, are there questions on how we executed this example here? Okay, so I'm going to do a little extra example here, and I think I've left enough space so I could do it here, but you might grab a scrap piece of paper. I want to just be, I want to kind of, I guess, draw your attention to a potential pitfall that we can get into when we're finding higher derivatives. So, we were able to find f prime, if we rewrote it, right, by bringing the, 1 minus x up to the top, and we didn't have to use the product rule, and that same thing, worked really well for finding the second derivative. What if my function, I'm going to just make a really slight change to the function they gave us. Instead of 2 over 1 minus x, it's going to be 2 over 1 minus x squared. Now, when we find the first derivative, the same technique will work, right? There's no x on top, so it's to my advantage to bring that bottom up and write it as a product, and then I don't even have to use a product rule or anything. So I write this as f of x equals 2 times 1 minus x squared to the negative 1. And then when we find f prime of x, who wants to start us off?
Negative 3 times 1 minus x squared
Times what?
negative 2x.
Negative 2x. Yeah, so the negative 2x, right, that's the derivative of the stuff inside. So now we have to be a little careful. I'm going to clean this up just a little bit. So we got a positive 4x, 1 minus x squared to the negative 2. Here's what I want to point out right now. There is no way to avoid using either a product or quotient rule now, right? Having used the chain rule, introduced a factor of x, right, into this other factor. So when I use, when we stop, if I'm finding higher derivatives, right? Like if I'm finding the second derivative, my first step is obviously find the first derivative. But when I find that first derivative, I'm going to stop myself and be like, okay, now how do I find the derivative of this? Right? So sometimes people get in the groove of just saying like, oh, the same technique will work, the same technique will work. But this one here, we have to use a product rule, or if we like, we could use a quotient rule. Either way is fine, right? But I can't avoid having to use either a product or quotient rule here. So let's say we use the quotient rule. I'm going to do some stuff off to the side here. My f function would be 4x, and so f prime is 4. My g function is 1 minus x squared squared. So g prime is what? 2. Bring the 2 down. 1 minus x squared to the first times negative 2x. So that's a minus 4x, 1 minus x squared. Okay. So now if we put this together, right, the quotient rule is the one that goes g f prime minus f g prime all over g squared. So g times f prime, that's 1 minus x squared squared times 4 minus f g prime, so 4x times negative 4x 1 minus 1 minus x squared all over g squared. So that would be 1 minus x squared squared squared. Then we have some algebra to do, right? So there's I would say substantially a bit more work to find the second derivative than there was to find the first derivative. Nothing we can't handle. I'm going to clean this up just slightly up top before we do that step where we factor. So 4 times 1 minus x squared squared plus 16x 1 minus x squared all over 1 minus x squared to the 4th. We could take out the greatest common factor, which is, what can we take out actually? We could take out a 4 for sure. What else?
1 minus x squared.
And that's just 1 minus x squared to the first, right? So because when I compare the exponents, I take out the least power. So we take that out. And then what do we end up with inside the parentheses? Or brackets, I guess.
1 minus x squared plus 4x.
Yeah, and in fact, actually, it'll be a 4x squared, and the reason is I neglected, when I combined these, when I multiplied these here, I forgot to put the square on this. Right there. So that was my mistake. So it'll be a 4x squared. And then, we could do a little canceling here, right? The 1 minus x squared here, we'll cancel with one of those. And then we'll simplify the stuff in the bracket. So we have 4 times 1 plus 3x squared over 1 minus x squared cubed. So there's f double prime of x for this function. So here was an opportunity to get some practice with a derivative that involves a chain rule with a quotient or product rule. We did the quotient rule here. But our takeaway, like the thing I want you to be kind of take from this example is, if you're finding higher derivatives, after you find the first derivative, stop yourself and just sort of think of it as a function on its own, and reevaluate, how do I take the derivative of this? I can't tell you how many times I will see somebody go from this, they'll find the first derivative, and then they'll forget about the existence of like a product or quotient rule, and they'll just sort of multiply the two derivatives because they were able to do that with the first derivative, right? Like having to use the chain rule right here kind of switched up what we needed to do. What we needed to do to find the second derivative. Questions on that example? Okay. So I know what you're thinking. You're thinking, great, I mean, we're not doing anything new. It's just higher derivatives, and how do we make things more interesting? You're right that it's not really new. It's just a new concept that we could take the derivative again, I guess. But the way we make things more interesting always when we're doing differential calculus is we say, let's try it with the implicit function. So we are going to find the second derivative of y with respect to x. And it starts, as these types of problems generally do, by finding the first derivative. So I'm going to write out this equation, 2x squared plus 3y squared equals 6. And we're going to take the derivative with respect to x on both sides. That's how we approach an implicit differentiation problem. What do we get if we differentiate with respect to x? Times what?
Times dy.
Yep. Perfect. Great. Now there's factors of 2 everywhere. Like I'm gonna, or both these terms have a factor of 2. So I am going to just divide out by 2, just for simplifying purposes. If you left the factor of 2 in, that's fine. Now I'm going to go over here, do a little side work, and just solve for dy dx. So that means that 3y dy dx is equal to negative 2x, and so dy dx is negative 2x over 3y. I'm going to now just let that sit there. And you could kind of take the problem from there and use the quotient rule, but also what I'm going to do here, and this is a pretty common approach, is I'm going to start again from where I am right here, right? And I'm just going to differentiate with respect to x again. So when we differentiate with respect to x again, the derivative of 2x is obviously 2. And then this right here, this is a product rule. So our f function would be 3y. And what's f prime? Close. What variable are we respecting? Yeah. Our g function is dy dx. What should g prime be if g is dy dx?
P squared y over g is squared.
Yeah. Right? If g is the derivative of y, then its derivative is the second derivative of y. Okay, so let's put this together. G times f prime is, let's see, g times f prime means that I am multiplying these two things together. So I've got 3 times dy dx times dy dx. And then plus f g prime, that's 3y times the second derivative. And this is equal to 0. So let's just see where we're at right now. We have an equation that has the second derivative of y in it, and that's a good sign for us, right? We want to find d squared y dx squared, so we have an equation where that shows up. Now here's the thing. If I can express, if I'm starting out as we are up here with an equation that has just x's and y's, and if it's possible to find the first derivative with just x's and y's, it should be possible to find the second derivative with just x's and y's, right? Not x's and y's and dy dx. So what we're going to do, since we found that first derivative already, I'm going to take this and we're going to substitute for those dy dx's there. So we got 2 plus 3 times negative 2x over 3y times negative 2x over 3y plus 3y times the second derivative we could do a little bit of canceling, just a tiny bit, right? We can cancel that 3 with one of those 3's. And we end up with, right now, 2 plus 4x squared over 3y squared plus 3y times the second derivative. Now when we stop here, we have an equation now that has the second derivative of y and x's and y's. And that's it. And that's a really good sign for us. That means we're ready to kind of go do algebra to solve this for the second derivative. Now this is an equation that has fractions in it, and I don't want a messy expression that has fractions within fractions when I solve for the second derivative. So the first thing I'm going to do is clear denominators. I'm going to multiply through by 3y squared. So I'm going to distribute that 3y squared on the left side. When we do that, we get 6y squared plus, in the middle term, the 3y squareds will cancel, so we just have 4x squared plus now 9y cubed times the second derivative equals 0. Now we can subtract the 4x squared and 6y squared from both sides. Right now it's algebra, right? This equation is essentially linear in the second derivative, right? The techniques we use to solve this for the second derivative are the same techniques we use to solve linear equations. So we have 9y cubed times the second derivative is equal to negative 4x squared minus 6y squared. And the only thing left to do is to divide by 9y cubed. And it feels like once we do that, it kind of feels like we're done, but we're gonna see something kind of cool work out. I'm going to rewrite the right side here. Up top, I could factor, there's a common factor. I'm going to take out a negative 2. And when I take out a negative 2 from the numerator, what's left inside will be a 2x squared plus 3y squared. Now that in and of itself isn't that cool. But the premise of this problem, right, our assumption in the universe in which this problem exists is the one in which, I'm going to scroll up to the top here, is the one in which 2x squared plus 3y squared is always equal to 6. That's the condition under which we're doing all of this work. So if I see 2x squared plus 3y squared show up as an expression, that's equal to 6. I can make that substitution. It's not true always, but it's true in this problem. So down here, this 2x squared plus 3y squared, that's equal to 6. So we have negative 12 over 9y cubed, or if we reduce that, dividing out a 3, we get negative 4 over 3y cubed. And what's kind of cool about this, first of all, is that we were able to make that substitution. Now, it's not that that always happens every time you're finding a second derivative, but it happens often enough that I'm on the lookout for it. So when I think I'm kind of done, I just check out what is the equation that I started with, and does that afford me an opportunity to simplify this nicely? And what we kind of, some insight that we gain from this is that the value of the second derivative, if we were to plot this curve, the value of the second derivative would appear to depend only on the y-coordinate and not on the x-coordinate. Yeah. I can't, I'm sorry, I can't hear you.
We're having issues with Zoom on the screen that you're sharing, so I'm going to help. There we go. Never mind.
We're okay? Okay, sorry about that.
We're good. Keep going.
The second derivative, you know, the value of the second derivative appears to depend only on the y-coordinate and not on the x-coordinate. Now, we are going to... we're going to see like some applications or like how we interpret the second derivative more in the later chapters. But when we, you know, if you were to look at this curve, right, the equation of this curve, I don't know why, sorry, OneNote is being a little weird. The equation of this curve, 2x squared plus 3y squared equals 6. What kind of curve is that? That's an ellipse, right? Both x and y are squared, but they have different coefficients. So, and we can tell it's centered at the origin because there's no x term or y term. So if we were to plot this, it looks something like this, right? Oh, that's awful. Let me cheat a little bit. It looks something like this. There, that's better. Now the slope, you know, finding dy dx obviously would have to depend on both coordinates, right? Knowing just the x-coordinate or just the y is not enough for me to know what the slope is. And we found that when we found dy dx, right? That it depended on both the x and the y. Now what the second derivative kind of tells us in terms of like looking at a graph is, we're going to talk a lot more about this in the next chapter, but it tells us, you know, like the first derivative tells us whether a function is increasing or decreasing, right? Whether that slope is positive or negative. But a curve could be increasing or decreasing in a couple different ways. You know, here's two curves that are increasing. These are both increasing, but their behaviors are quite different. So what's different about these two curves is what we call the concavity, like whether it's concave up or concave down. And what we found is that the second derivative depends only on the value of y, meaning whether it's concave up or down depends only on the value of y. And that kind of makes sense if we think about this curve. It's obviously concave down for these values of y, right? And it's concave up for these values of y. So there's sort of like some graphical kind of interpretation or context to, why it kind of makes sense down here that the value of the second derivative depends only on the y coordinate. We're going to do a lot more with graphing and concavity in the next chapter. Are there questions on this example? Okay. So I guess where I'm at right now is we could take the rest of the time. I could let you have the rest of the time to work on the problem set or practice if you like. If you want, we could start working on, get a start on the next chapter. I guess I'll throw it out to you guys and see what you want to do.
I like to.
You'd like to work on the problem set. So that's fine. How about use this time to work on the problem set, and then tomorrow I'm really going to expect at the beginning of class, I hope, to get some questions. Like, I'm stuck on this problem, or I'm not sure how to start this one. So, that's how we'll start the beginning. That's how we'll spend the first part of the class. So make good use of this time that you have now. You've got, like, a half hour or something to start working on this problem set. And then at the beginning of class tomorrow morning, I'll expect some questions from y'all before we start talking about Chapter 3 material. Okay?
We're going to be a fun problem set right now.
Okay. All right. Well, then I will see you all tomorrow morning. Enjoy the rest of your day.